Good afternoon. My name is Flávio Assis. The title of my presentation is Simple Area Coverage by a Dynamic Set of Unmanned Aerial Vehicles. All the authors of this paper are members of LACID, the Distributed Systems Laboratory at the Federal University of Bahia. And this work is basically the main results of Grazieno's master dissertation together with the work of Gustavo, who is an undergraduate student of the computer engineering course also at UFBA. So I'm going to talk about UAVs, unmanned aerial vehicles, and these vehicles have become an important tool in many application scenarios, like for example agriculture, surveillance, monitoring, and so on. The benefits of these devices are naturally potentialized when they are used in groups, and these groups of UAVs are commonly called swarms. UAVs are being used as a tool to solve problems and that we consider as members of a class of problems that we call area coverage problems. But how do these problems look like? What are these area coverage problems? Let's suppose that we have an area of interest, and I'm showing here in this slide a picture of our campus in Salvador. And let's suppose that we want to use UAVs to build a two-dimensional image or a three-dimensional image of the whole area, or for example, to use UAVs to monitor the area for some security purpose. A common approach is to see the area as being structured or divided into a grid, and the UAVs will fly over the area, and when they do so, they sense or they use their sensors to capture some information about the area, like for example to use a camera to take a picture, or to use a gas detection sensor, a gas sensor to detect the gas in the area, and so on. So there are many problems that we have. We might call them area coverage problems, and we think that many of these problems have a lot of aspects in common, but they also have many particularities which differentiate them from each other. And different problems require normally different approaches. Our goal is to create a framework to study strategies to area coverage problems, in particular with dynamic groups of autonomous UAVs. By a dynamic group, we mean that new UAVs may enter the group of UAVs accomplishing a certain mission, or UAVs may leave this group. We are first studying a particular problem that we call simple area coverage with dynamic swarms. I will introduce this problem shortly. And in this presentation, what I'm going to do is to present a specific strategy to address this simple area coverage problem, to briefly introduce our framework that we are building to implement strategies to area coverage problems, and also to present or introduce metrics to assess the quality of strategies to area coverage problems. The simple area coverage problem with dynamic swarms can be simply described. We have as input a grid representing an interest area, and we have a set of UAVs. In this slide, we represent 3 UAVs. And the UAVs will fly over the interest area, and they have to cover the whole area. What do we mean by cover the whole area? They must visit, or they must sense each of the cells of the grid. That is, all of the cells of the grid must be visited by at least one UAV at least once. We call, when a UAV moves to a certain cell, we say that the UAV visits the area, and this is a way of abstracting from what is exactly the mission of the UAV, to take a picture, to sense gas, and so on. We just call that cell is visited. And while they move over the area, they can communicate with an external device that we call base station. And communication between the UAVs and the base station, we assume that is possible at any time and through reliable wireless communication channels. These base stations, the base station is a device which can collect information from the UAVs and can coordinate their actions. In particular, we want to address dynamic aspects of the group. And then some of the UAVs might crash, or we might have new UAVs being added to the group. This problem has three main sub-problems. The first is how to divide the area among the UAVs. The second problem, is once an UAV has a region to cover, how will it traverse that region? And the third problem is how to address the dynamic aspects of the group. There are many additional issues that could be considered, like, for example, how to handle faults, and in particular, how to guarantee a group consistency in the presence of faults. But some of these issues are not being considered at the moment by us. We divide the area, that is, we address the first problem by using Voronoi diagrams. A Voronoi diagram has as input a set of reference points, and these points are represented by these dots in these slides. And a Voronoi diagram divides the plane in regions in such a way that a region where a reference point is corresponds to those points in the plane who are closer to that reference point than from any other reference point. That is, Voronoi diagrams divide the plane based on distance, proximity. How is it related to our context? Our reference points will be the current positions of UAVs, and once we have the Voronoi diagrams and the grid, it's determined which cells have to be visited or covered by each of the UAVs. How do you address the second problem? How do UAVs traverse a given region? We use a simple method called Bolster Freedom, and it's represented by this red line in the slide. And starting from a starting point, the UAV moves north until it can no longer move north, and then it moves one step east, and then it moves south until it no longer can move south, and then again one step to east, and repeats this movement until it can no longer move using this approach, either because it has reached the border of the area, or all the neighbor cells have already been visited. And then in this case, it resumes its execution from a non-visited cell, which is most to left and south, most to west and south. So how do you address changes in the set of active UAVs? We simply recompute the Voronoi diagrams in the event of UAVs leaving the set, UAVs entering the set, or when a certain UAV has covered its whole region. Then it has to move to a previously non-visited cell, and then a new Voronoi diagram is computed, and the UAVs resume their execution assuming the newly computed regions. Then in the picture we show here a newly computed Voronoi diagram. Consider the new positions of UAVs, the failure of one of the UAVs, and a new UAV being added to the group. So our implementation framework is based on ROS Gazebo. ROS Gazebo is a tool or a set of tools often used by the robotic community, and it provides a very nice simulation environment with functionality to simulate the physical behavior of robots, including UAVs. On top of ROS Gazebo, we have implemented a layer called Drone Middleware, which provides a programming interface which eases the development, or the creation and monitoring and tracking of simulations with more than one UAV. But the drone middleware controls and tracks the execution of UAVs individually. Then on top of the drone middleware, we have implemented the software components needed to coordinate the multiple UAVs to solve the area coverage problems. In particular, in this layer, we have implemented a component called coverage maps, which are representations of the grid, and but with and coverage maps represent which cells have already been visited and which cells have not been visited yet, and this information can be used to coordinate the actions of the UAVs in the group. But once we have designed a given strategy to solve some of these problems, how could we assess the quality of the strategy? To cover the area is not exactly the problem. The problem is how well can we cover the area considering the set of resources that we have. For example, the set of UAVs that we have at the moment. Then we think that a good strategy obviously has to cover the whole area, but should also minimize the time needed to cover the whole area, and should provide low movement redundancy. Our strategy clearly always covers the whole area, because UAVs move to previously non-visited cells until all of them have been visited. But how well does our strategy cover the whole area? So then using our framework, we used our framework to implement this strategy, and we have first computed the mean time to cover. We implemented or evaluated scenarios using from 1 to 8 UAVs. And for each number of UAVs, we consider 3 scenarios. One with no insertions of UAVs in the group and no removals of UAVs from the group. A second scenario with 1 insertion and 1 removal, and 1 scenario with 2 insertions and 2 removals. And we can see in the slide here, for example, that the decrease in time to cover the region, we have a strong decrease when we go from 1 UAV to 4, but a not so strong decrease in the time to cover when we go from 4 to 8 UAVs. So, but how do we evaluate the movement redundancy of strategy? Then we introduced movement color maps. A color map is a representation of the grid, and we assign a counter to each cell of the grid. And this counter is incremented each time an UAV visits the cell. And we use a set of colors, a range of colors from a light color to a dark color. And darker colors represent more frequently visited cells, and we can then see, we have a visual tool to evaluate how was the movement pattern of our strategy, and evaluate how redundant or not the solution or the strategy has been in terms of movement. So, to conclude the presentation, we think that we have started studying particular issues involved in the development of strategies to area coverage problems. Although we have used some techniques that have already been previously used in some related work, we are not aware of a thorough discussion of the issues involved when we have dynamic groups of UAVs, and we are aware that many additional issues demand further investigation, like, for example, how we address communication failures and partial communication between UAVs, or the design of a fully distributed strategy for the program. These are future work. Then, thank you very much.